I guess we'll go ahead and get started. We're going to pick up exactly where we left off last time. We were dealing with a question from the homework about what does it look like when you protonate formaldehyde. And what should you predict? Should you combine the bent CH2 with a linear OH group, or should you think about trying to somehow make the OH group bent? We were sort of asking ourselves whether the final structure should be something like this, which looks weird because you've never drawn it that way in sophomore organic, or something like this, which makes more sense, presumably because the proton is in the place of one of those rabbit ear lone pairs that we've always thought about. But we've learned recently that the lone pairs on oxygen are not equal in energy. There's one that's P-rich and there's one that's S-rich. And so we're a little bit confused and not sure what to do. So we began, like the text encourages you to do, start with the higher symmetry molecule. Start here. Generate the orbitals there, and then distort to get the lower symmetry one and see what happens in terms of orbital overlap and what you can predict in terms of energy. So our alphabet of orbitals that we can bring with the group, the methylene group, is the sigma CH3, the pi CH3, the sigma out, and then the unhybridized p orbital. And then the alphabet we bring from the linear OH group is an orbital where you have the 2s on oxygen overlapping with the 1s on hydrogen. The out of phase combination is probably empty, high in energy, so we won't worry about it. You can account for one of the p orbitals on oxygen also overlapping with the 1s orbital on hydrogen. I'm not showing you the antibonding combination there. And then you have left over two p orbitals that are orthogonal to this one. This one lies along the bonding axis between oxygen and hydrogen, and these two are orthogonal to that. Okay, so those are what we can bring to bear on this problem. And last time we started to show you some of the combinations that you could get. So if we add the sigma CH3 from and hi Dakota, you can, I think we can maybe hear you. You can speak up if you have a question, or wave like this at the screen, because we can all see you, and the students here will tell you, tell me that you got a question. We can, let's see, bring together the sigma CH3 with the s orbital derived OH group. We could then do this out of phase combination of those two. And so far, this looks very much like what we've done before with two methyl groups coming together or two CH2 groups coming together. So I guess I'm going to erase this one since that's an out of phase combination we're not going to use. So we get these two MOs from the combination of this sigma CH3 and this linear sigma OH group. Okay. The next one we could get by combining the sigma out of the CH2 group with this sort of p orbital derived orbital from oxygen. This is the in-phase combination. The out-of-phase combination would be high enough in energy that we don't need to worry about it. And then we can combine the pi CH3 with the p orbital that lines up in the appropriate direction, and then the p orbital on CH2 with the corresponding p orbital on oxygen, and that's sort of our pi bond. And then you also have the out-of-phase combination of the pi CH2 with the p orbital that lines up with it. If we think about how many electrons we have, that'll tell us how many sort of bonding orbitals we need. 2, 4, 6, 8, 10 electrons plus 2 more on the oxygen. That's 12. Am I right? That's 12? Okay. So we're going to need 6 orbitals, and we have 6. Ordering them in energy is going to be difficult, and so we're not going to worry about their relative order in energy. But we might be interested to know whether to expect the geometry to be linear versus bent. And so what we're going to do, and what we did at the end of class last time, is we started to make systematic distortions from linear to bent, and we tried to see what that would do to orbital overlap. All right, so if we had to think about going from this linear arrangement to a bent arrangement, what would we predict here? Probably not a huge change. There's not really a huge change in orbital overlap. I suppose you could argue, well, now maybe the hydrogen can see the other hydrogen better, but that's such a long distance that I don't think it would make much of a difference. So we're going to imagine that there's not much change there. What that means is that the electrons that are in this orbital are not going to be strongly stabilized by distorting geometry. So this isn't going to give us an explanation one way or the other. Similarly, we might say the same thing for the out-of-phase combination. And again, I'm not showing these in order of energy. We're just showing you relative to the linear thing, the linear geometry, what we would expect the energy of any given orbital to do. And again, it does not appear that there should be much change as we go from linear to, I guess, bent. Okay. All right. What did we do for, let's see, the place where we started to see some change was when we considered what would happen to the pi plus p orbital combination. And we noted that if you bring that hydrogen out, that's a nice sound, of the plane of the node here, that you can now get productive orbital overlap between the hydrogen in pink and the corresponding lobe on the oxygen p orbital. So what we predict there is we have increased oxygen-hydrogen bonding character. And that ought to decrease our energy. By how much? Don't know. Wouldn't ask you to predict it, but by some amount. Okay? So far, what we have predicted is that for 3 of our orbitals, for 2 of the 3 that we've done so far, there's not much change, but we found some strong stabilization in one of them. All right. Let's think about what would happen to the sigma out orbital if we change the geometry. Did we do that one last time? All right, this lobe on the left of the sigma out orbital really came from the p orbital on oxygen overlapping with the 1s orbital on hydrogen. So probably moving to the, sorry, I don't know where these lines are, probably moving to the sort of bent geometry decreases to some extent the orbital overlap between oxygen and hydrogen. So you might expect this one to get a little bit higher in energy, but probably not a huge amount. And remember that the sigma out orbital is likely to derive most of its stability from the overlap between the carbon and the oxygen. In terms of the pi bond that comes from overlap of the two p orbitals, there should be really no change at all, because the hydrogen that we're talking about is in the plane, is in the node, lies along the plane that's part of the node, and so you would expect to see absolutely no change there. And then finally, let's see, the last one on our list, and again, this isn't necessarily in order of energy, but if you look at the last one on our list and then think about bent geometry at that oxygen, I'm trying to erase extraneous stuff. Again, moving that hydrogen out of the node would allow us to get favorable orbital overlap between the lobe on the oxygen and the hydrogen. So we would see, again, increased oxygen-hydrogen bonding character. And that would allow us to predict some amount of stabilization. Now, we haven't dealt in any absolute energies so far. And you might ask, well, the increased orbital overlap we get here and here, shouldn't that be about the same as we lose here? Okay, fine. We can make that a little higher in energy if you want. But if you look at the overall changes, what's occurring when we go from linear to bent, we see some decreased oxygen-hydrogen overlap. But then we have two orbitals where we see increased oxygen-hydrogen overlap. And if I were to guess, I would say that the two increased oxygen-hydrogen overlapping interactions probably more than compensate for the decreased oxygen-hydrogen overlap in the sigma out plus p orbital. All right, does that sort of make sense how we've walked our way through that? Systematic variations. Go ahead, Austin.
Earlier we said that we weren't going to use the oxygen-hydrogen out of phase orbital.
Right.
But in my mind, that looks a whole lot like one of the oxygen p orbitals.
Huh.
What's the justification for using the p orbital but not?
Oh, so you're thinking if I had the oxygen-hydrogen out of phase. Sorry, I'm trying to figure out what to do. I got to put it back there. Oops, didn't want that.
Specifically looking at how that sigma out p combination is.
Yeah, it actually looks like the only difference is here you have a node in between the oxygen and the hydrogen, whereas here you don't. So I think that's the only indication that you would want to use that one. All right.
I guess either way it's still one node, right?
That's right. You're right that either way it's still one node. The difference would be that this one has bonding character, whereas this one doesn't. Yeah. All right. So I told you I would do the calculations on this. Other questions? No? Yeah, Kim.
It seems like somewhere in the book you talked about, like, it also matters the number of electrons that are going down and up. So if you don't use it just because, like, 4 electrons are being stabilized while only 2 are being stabilized.
Exactly. Yep. Yeah, exactly. You have 2 being destabilized, 4 being stabilized. Depending on the exact numbers, you could go either way. It turns out that the lowest energy state for our molecule is the one that the bent structure that we've shown you on the left, right. Sorry, I don't know my left or my right. So I'm going to try to show you the orbitals that we get from the actual calculations. So there's the sort of S-rich sigma orbital, encompassing everything, no nodes. Similarly, there is, and there are some directionality and shape to these orbitals that we haven't predicted that I wouldn't expect you to, because I certainly couldn't do it, but the one we've shown here is that one from the calculations. And I started this, actually, I submitted the linear geometry to Gaussian, and it came back with this bent geometry, which tells you that that's the more favorable one. Let's look for the sigma out combination. I already dealt with that one. And this one's weird.
Didn't it have 3 nodes? Wasn't it that one on the left?
The sigma out combination should yeah. No, this one looks kind of like the pi one, right? Okay. The
One in the middle there?
pi bond here is, oh, sorry. This is the pi, p plus p. What are we looking for? Regular pi and sigma out. This would be the pi star, which we don't need. It kind of looks to me like that one goes there, and then maybe this one is the sigma out. It looks like it's distorted, honestly. It looks like the orbital density here is sort of overlapping with the orbital density there, and then you have this lobe here that's sort of distorted and moving up. So it gets a little hairy with some of them, but it looks overall like we've come to an answer that's pretty similar to what we get from the calculations. So my goal in this section is for you, when someday you're doing a calculation on something or you're seeing some molecular orbitals, your first response is not what the heck, but rather, okay, that looks like it could be a pi group orbital from that CH2 group, and then something else. Okay. All right. What more do we need to say about that? No? Good. Because we've gone through that, I'm not going to show you how to go through formaldehyde because it would be pointless. I'm also not going to show you how to go through ethylene and get the double bond because that's easy, and so you can see that in the notes. Next, we're going to start using orbital mixing approaches to get a sense for rules of thumb that we've developed over time. We'll talk about some reactive intermediates. We'll also talk about pi systems. So the one I wanted to talk about was what happens when you have, say, a pi bond, and you want to replace one of the hydrogens with a methyl group. What mixing could you do? Now, you could do all of the mixing, but sometimes it's useful to just focus on some, okay? So your text has you think about mixing group orbitals from the methyl group, pi orbitals from the methyl group, with pi orbitals from the double bond, all right? So if we were to think about what the pi orbitals from the double bond are, you've got sort of the p plus p combination. You know what? I thought I could do without color, but the answer is no. Why don't I do something other than pink and yellow? Well, when you run the class, you can choose different colors, is my answer to you. All right, so you've got the p plus p. We used to call that the pi orbital. You've got the p minus p for the olefin part, the olefin fragment. And then over here, you've got your methyl group. And let's see, it will turn out that it'll be easier for us to get the appropriate orientation if we draw this methyl group in a little bit different way. What we're basically doing is we're taking this kind of orientation and we're grabbing the hydrogen on the bottom and swinging it up to be sort of pointing out at us but horizontally. This hydrogen is going to stay tipped back and this one is going to be tipped back. That's going to give us overall this type of arrangement. And the reason we'll do this is because we're going to be using the pi orbital that has that hydrogen that's sticking out at us in the node. Okay, so do you remember there was a pi orbital from the methyl group that looked like this? Sure. Okay, and so that would have been the, we called that the pi CH3, and then we would have also had the sort of out of phase combination. Oops. All right, so let's just start by remembering that the p plus p orbital is low in energy. It's a bonding orbital, and so is the pi CH3 orbital. The p plus p orbital has carbon-carbon bonding character, whereas the pi CH3 orbital has carbon-hydrogen bonding character. So you can imagine, and we won't worry about their relative energy levels. I would predict that the pi CH3 is going to be lower in energy because it has S character from the hydrogens. So, you know, we could put it here, but it doesn't matter how far down we're putting it. If we were to mix these three together, notice how, or these two group orbitals together, notice how they can overlap in phase. And, you know, we're going to say it goes down somewhat in energy. We won't say by how much. We'll notice that the combined orbital that we draw should probably be more on carbon than it is on, more on the methyl group than it is on the pi bond. But you can see that if you were to look at this molecule, which happens to be propene, you would expect to actually see a pi orbital delocalized over the whole molecule sitting on that methyl group too. All right. Let's see whether that actually works by going to Spartan, which does not wish to comply. Come on, there we go. See what those orbitals are and see if we can find a pi orbital that extends over the whole molecule. Oh, how about that? What the heck is that? Well, that is the combination of the pi CH3 with the p plus p orbital in the double bond. That's totally interesting, right? Because that means that what we thought were our pi electrons are more on the carbon than they are on the, and more on the methyl than they are on the pi bond. Okay, but does that explain the real reactivity of the double bond? Because what about the antibonding orbital combination? Again, how much higher should it go in energy? Not sure. The out-of-phase combination should be correspondingly more on the pi bond part of the molecule than it is on our methyl group. So we'll indicate that with sort of smaller coefficients on the methyl group and more coefficients on the olefin carbons. Well, oh dang. Okay, so go ahead.
Would they be in phase as you have them there for the antibonding, or should they be out of phase?
So we are mixing this pi orbital with this p plus p orbital. We'll mix those two together in phase and out of phase. We won't change any of the phase relationships within each group yet. So in this case, they overlapped in phase, and this is out of phase, where there's a node right there. Okay, so if we think about this molecule coming together, we have electrons associated, and this is going to, the argument here is going to get a little bit hairy because what electrons came from where. In our pyramidal methyl, we would have had electrons in a pi type orbital. We would also have had electrons in this p plus p orbital. You bring them together, and what looks like happens is the electrons from the methyl group go down in energy and get to spread out a little bit, which is exactly what we see from Spartan. The electrons are still mostly on the methyl, but they're spreading out a little bit into the pi bond. Similarly, you see that the electrons that were in the pi bond get higher in energy. Okay. What does that do for us? Well, let's see if we can find the pi electron orbitals. Okay. Whoa, what does that look like? There's our methyl group here. Here's our pi bond. That should look very similar to what we drew for the group orbital combination of what the HOMO of our molecule is. Okay. Incidentally, this is one of the reasons why more substituted alkenes are more reactive. In terms of valence bond theory, you can think about alkyl groups being electron donating groups, which is fine. But in terms of the MO picture, having that methyl group actually pushes the pi electrons up in energy. We could do a similar thing with the antibonding orbitals. We could combine them in phase and out of phase. And I won't necessarily show you, well, I'll show you one of the options. probably the pi star is lower in energy than the antibonding pi CH3 for reasons we don't necessarily need to go into. It has to do with the orbital overlap that generated this orbital versus that one to begin with. In any case, when you mix these two orbitals in phase, you're going to get a lowest energy unoccupied orbital that is mostly still the pi star. But which still has some characteristics of the methyl group. We're still going to have some of that orbital density out on the methyl group, and I can draw that here. We'll draw a smaller coefficient on the methyl group, fill in the phase relationships. So for our propene, this is the LUMO. And I'm sorry that the picture is kind of crowded. When I draw slowly in my office for my own notes, it's a lot prettier than when I draw fast in class, and I apologize. Yes, end of semester evaluations. Poor choice of color on in-class drawings. What this tells you is some of the LUMO is actually on the methyl group, and in particular on those methyl protons. All right. So what would we, how can we see that here for Spartan? Yeah, we see there's the pi star. We see some actual overlap between the carbon of the methyl group and the carbon of the first carbon of the olefin, sort of a pi bond-like thing here with orbital density on the two hydrogens. Okay, I showed a diagram like this. I showed an image like this in 351 once to talk about how some of the LUMO is on those alpha protons, and the question was asked, why are they different in phase? Now we know actually why they're different in phase, because that LUMO comes from the combination of the antibonding pi CH3 with the pi star. And that's, of the two possible combinations, that's the lowest energy one. Now, one question that your text brings up at this point, does this represent hyperconjugation? No. Hyperconjugation is a valence bond theory concept, which we'll talk about. Hyperconjugation is overlap of a filled orbital with a empty orbital in the same molecule, but it requires you to be dealing with orbitals that are localized either in between bonds or on specific atoms. In terms of molecular orbital theory, hyperconjugation is just like resonance. You don't need it to explain things because the electrons are delocalized. Nevertheless, what we would say in terms of hyperconjugation from a valence bond theory model would be that the filled carbon-hydrogen bond can overlap with the adjacent pi star and donate electron density into it. So that's orbital mixing of a kind. Though notice here, we're not mixing empty orbitals with filled orbitals. We were mixing filled orbitals with filled orbitals. We used hyperconjugation in 351 to explain why more substituted olefins are more stable. Here in our MO picture, it looks like the substituted olefin is less stable, but remember, I've only showed you one orbital mixing interaction. I haven't shown you all the others. And when we're thinking about the stability of the molecule, we have to think about all the electrons. Right. So, for example, in our lowest energy orbital for this molecule, you would expect that orbital to be over this all-in phase sort of combination of s orbitals to be better for propene than it is for just ethylene, because you've got more atoms in it and the electrons are delocalized over more space. And we could make similar arguments for a lot of the other orbitals. We won't worry about that. But yeah, there we go. So one of the neat things that I want you to see is that combining group orbitals to get new orbitals for new groups can lead you to the same kinds of conclusions that you've gotten before from valence bond concepts like resonance and hyperconjugation. Other questions you want to talk about that? Okay. What if, should we do a carbocation? I'm not sure I want to do carbocations yet. Thinking about bringing two molecules together, we can actually start to derive orbitals for pi systems through the same sort of combined group orbital approach. So 1,3-butadiene. Before, when I've taught how to get the pi orbitals from 1,3-butadiene, I've said, okay, you've got 4 atoms, you've got p orbitals on adjacent atoms, let's combine them in all possible combinations. And that's fine. Conceptually, though, you could consider combining the two orbitals, the two pi-type group orbitals for ethylene, which again would be the pi and the pi star. I don't know why these p orbitals are stylistically slanted, but that's what we're going for today. All right. Technically, filling in the yellow here is superfluous because we could already see the difference in phase by shading one of them, but like I said, when you're in charge, you can do what you want. If we do the in-phase combination of these two, we get just what you would expect for 1,3-butadiene. Dang it. Hurrying is never a good thing. All right. Versus the out of phase combination, which you would get by doing this. Okay, pretty straightforward. Easy peasy. And then we can get the second set. And this one's kind of weird because actually if we bring the two of them together just as we've drawn them, that's actually the out of phase combination where the two central atoms overlap out of phase. Whereas if we switch the one on the right, we get in-phase overlap between those two central atoms. Right, so here's our starting orbitals. And so automatically, this picture of the pi orbitals in butadiene comes from mixing the two mixing the group orbitals associated with the pi bonds together. And of course, we can fill these in with the available electrons and then assign HOMO versus LUMO. And you already knew what the orbitals of 1,3-butadiene were, but this was new to me in terms of how to get them. It's just combining simpler pieces together. Where this gets really useful is when we start dealing with Allyl type pi systems, which you can then use to build aromatic systems. Any questions about the butadiene system, though? Boring, right? Okay. Allyl may seem like a step back because it's smaller. Of course, if we do allyl cation, you should be familiar with the fact that resonance tells you that the positive charge is on carbons 1 and 3, but never on carbon 2. One of the ways we can derive the orbitals for allyl, which has made more sense to me than anything I've ever done before with this system, is to start by combining, mixing the two p orbitals on C1 and C2. All right? So here's the 2p orbital on C1, and we're going to mix in all possible, we're going to do a linear combination of atomic orbitals with the 2p orbital on carbon 3. We'll do, in phase and out of, whoa, we just blew up wave functions there. In phase and out of phase. Now, you mix these two together, and we can do this via the same type of energy diagram we've done before. Only because those two orbitals are far apart in the molecule, they're not adjacent to each other, they don't overlap at this stage. So we just end up getting two degenerate orbitals. One that looks like this, and the other that looks like that. And they look exactly the same except for the difference in phases. So far, there's no change in energy because there's no overlap. Though we will notice that the second orbital we drew has a node, no orbital density on carbon 2. Then, now we add the third p orbital. So essentially now we're going to have these be our starting orbitals, and we'll mix both of them with a p orbital on carbon 2, both the plus and the minus combinations. So if we do that for this first one, we convert what was a not bonding orbital into one that's a decent bonding orbital, right? Because there's in-phase overlap on adjacent atoms. The out-of-phase combination involving these two gives us the highest energy version. Okay. And then what about trying to mix these two? Well, you can't, because carbon 2 is on the node there. So there can't be any orbital density on carbon 2. There can't be any mixing of carbon 2 with this second orbital that we've got, so it just stays unchanged. And then you have your 3 pi orbitals. And depending on whether this is allyl, anion, cation, or radical, you can determine what the HOMO or the LUMO is. If it's allyl cation, the LUMO is that empty orbital on atoms 1 and 3, which is exactly what resonance tells you. All right? There is a problem in your study guide that I was talking about with Kim before class. It was kind of challenging. The question was, what if atom 3 is oxygen? What if this is an enolate instead of, say, the allyl anion? So if this is the allyl anion, we would have electrons in this second of our 3 pi orbitals. This would be our highest occupied molecular orbital. The question is, what does that do when we replace one of the carbons with oxygen? And it's sort of conceptually hard to mix 3 things in the same way that we've mixed 2 before. But the principle that we've learned is that when you first, that orbitals that have that molecules that have the same shape, symmetry, have the same qualitatively similar orbitals. So the pi system orbital should be basically like this, but there will be a distortion because oxygen's lower in energy than carbon because of its lower electronegativity. Now remember what we did before with, I believe this was last time with methyl chloride. We talked about how the bonding, when 2 orbitals are different in energy, the bonding orbital resembles the lower energy atom, whereas the antibonding orbital resembles the higher energy atom. Based on that argument, you would predict that in the enolate, the lowest energy orbital should be more on the oxygen than on the carbons. And then in the other 2 orbitals, the other 2 orbitals should be more on carbon than on oxygen. Right? You're mixing 1 oxygen with 2 carbons. So in the lowest energy orbitals, got to resemble oxygen, and the other have to resemble the 2 carbons more. And this is, if you do the calculations, the numbers bear out. In the enolate, in pi 2 of the enolate, there is a larger orbital coefficient on the alpha carbon, which is why enolates, in most cases, at least in the aldol reaction, carbonyl chemistry, enolates react a lot, mostly at the alpha carbon instead of the oxygen. All right. With these 3 allyl orbitals in hand, we can do benzene. And this was really fun to me because I've never been able to explain before to my 351 or 352 class where those strange looking benzene degenerate orbital pairs come from. But it's actually really easy when you think about benzene being the combination of 2 allyl groups. As an example, here's the lowest energy orbital from one allyl group. Here's the lowest energy orbital from another allyl group. Oh, I don't like it because there's no color. Put them together in phase. What do you get? We're going to take the view from above, which is simpler. You get the all in phase combination from benzene, and if you put them together out of phase, you get the first of our 1 node orbitals. Does that sort of make sense? Okay. What about combining those intermediate, the pi 2 orbitals that look like this? If we do that in phase, boom. What used to be a bonding orbital, a non-bonding orbital, is now a bonding orbital because you get productive in-phase overlap. And surprisingly and accidentally, surreptitiously, who knows, this orbital has 1 node. It has the same number of bonding interactions as the higher, as did the minus combination of the pi 1 type orbitals. So these are degenerate. Okay. If we do the out of phase combination there, we then get one of the 2 higher energy empty orbitals in benzene, where we now have 2 nodes. And then finally, if we take the pi 3 orbitals that are all out of phase, and I apologize for the crudeness of the drawing because of the hurry that I am in. If we combine the two pi 3 orbitals in phase, we end up with this orbital with 2 nodes. These 2 are degenerate, and then the minus combination would give you the all out of phase option like this. Okay? Yes, Kim?
So in that case, you like use the number of nodes to decide when things are degenerate or not? Which
Yeah.
we haven't been able to do with other things.
Mm-hmm.
How
Well,
do you know when you can use
why
nodes?
are we doing that here? When can you use nodes? I believe it works best. The times where we've been a bit confused is when we've looked at nodes between sigma type and pi type orbitals, where the kind of overlap is qualitatively different. End-on-end overlap is different from side-to-side overlap, and so the nodes isn't the whole picture. But these are all pi orbitals with same symmetry, same extent of side-to-side overlap. So in this case, nodes differentiates them perfectly. And that will be generally true for pi systems. Okay. Now, a fun exercise might be for you to generate MOs for acrolein, which is this enone, using the group orbitals from, and just do the pi system, do the pi orbitals from ethylene and from formaldehyde. And knowing what you know about oxygen's electronegativity, see if you can determine where the LUMO should be, where most of the LUMO should be. Because as you'll recall, with alpha beta unsaturated carbonyl compounds, you have the option of attacking at the carbonyl carbon or at carbon 4. And so see if you can, by MO group orbitals bringing together, see if you can come up with an argument about whether, see if you can tell whether attack at 2 versus 4 might be preferred. All right, I guess that does it for now, so we'll sign off.